right. Hi there. My name is Nell Wallachek, and I'm the software engineering lead of the WebVR team here at Microsoft and a WebVR spec editor.
Good day, my name is Lewis Weaver, and I'm a program manager for the WebVR team at Microsoft. So today, if this clicker button works. There we go. All right. Today we're going to give you a quick overview of Windows Mixed Reality, followed by a discussion of the new WebVR specification, which has been available in Microsoft Edge since the Windows Creators Update in April. We'll show you how to build your own WebVR experience, introduce you to some helpful libraries, and touch on some good practices and tips. So let's get started. Several weeks ago, Microsoft announced that beginning on October 17th, a variety of Windows Mixed Reality headsets and motion controllers will be available from Lenovo, Dell, Acer, HP, and Asus. These immersive headsets deliver built-in inside-out tracking, meaning there is no need to purchase or install any external trackers or mount sensors on your wall. There's no complicated setup, it's just plug and play. The Windows motion controllers offer precise and responsive tracking within your field of view. Also, no additional sensors are required beyond those already in the headset. So, what is the experience like? Great. So now we've seen the mixed reality devices and software in action. So how can we bring this technology to the web? The answer should surprise nobody in here. It's WebVR. To quote, WebVR is an open specification that makes it possible to experience VR in your browser. The goal is to make it easier for everyone to get into VR experiences, no matter what device you have. And I'd also like to add another goal, which is to make it easier for developers to reach all possible users with their code. But what does it actually look like for these users? Let's imagine for a second that you're planning a vacation and you're browsing the web trying to decide which hotel to stay at. While looking at some photographs of available rooms on one hotel website, you notice a button for viewing the room in VR. So from right there in Edge on your Windows 10 desktop PC, you click the button, you don your immersive headset, and without installing an app, you are now immersed within and looking around your hotel room. You can really get a sense of how big, or in this case, how small that bed really is. We just showed you how seamless it is to get into WebVR from Edge on your desktop. But wait, there's more. Remember that first video we showed you of the Windows Mixed Reality Cliff House? Here is Edge running within that Cliff House. You can view any website, your favorites list, multiple tabs, in private browsing, and more features. And the transition into immersive experiences on websites that support WebVR is even more seamless since you're already wearing the headset. The potential uses for this technology are vast. Here we list a couple of examples: tourism, real estate, online shopping, 360 photos and video viewing, gaming, and much more. And the most exciting part about all of this is you can start enhancing existing websites with this technology today. Dev kits are available from the Microsoft Store, plus there is a built-in headset simulator as part of the Windows 10 Creators Update, which, as I mentioned, came out last April. Other browsers have also been implementing this technology. As such, there is now a released browser with WebVR support for every mainstream headset there is. There is further support in Servo, which is Mozilla's embedded browser, and a custom Chromium build, which is available on desktop and mobiles. Compatible smartphone browsers can also support WebVR through cardboard-style viewers.
Great, so WebVR works everywhere, but you may be asking, how does it work? Immersive headsets are a combination of displays and sensors, and the WebVR APIs are providing the access to that data. The headsets themselves are represented by VR display objects. To find out the resolution you'll need to render to for each eye, you'll use the getEyeParameters API. To get called back at the device's refresh rate, you'll use the request animation frame on the VR display object. Those of you familiar with window.requestAnimationFrame, this is not the same thing, and we'll talk about why in a little bit. And to actually find out where the headset is in space on the matrices you'll need to do your rendering, you'll call the VR display's getFrameDataParameters. One question that we get asked frequently is, how does WebVR relate to WebGL? And the answer is that without WebGL, there wouldn't be WebVR. WebVR tells us about the headsets, and then we use WebGL to actually render the pixels that will get displayed to the headset. The two specifications go hand in hand. Okay, so let's actually take a look at how the functions I mentioned from before are actually used. To display WebVR content, the first thing you'll need to do is query for an available headset. Then you'll need to request access to use that headset. Then you'll actually draw, and when you're done, you can return to 2D. Let's take a look at that first step. The first function to pay attention to here is this navigator.getVRDisplays call. It returns a promise, and when the promise completes, you'll have received the set of available headsets. On supported mobile devices, there'll be one headset. On supported desktop systems, there'll be 0 or the number of headsets that are currently connected and compatible with the system. You'll have to handle that accordingly. On systems that do not support WebVR, either the getVRDisplays function will not exist, or the promise itself will be rejected. In this case, it's safe to fall back to orientation APIs to make sure your experience can reach the broadest set of consumers. When the page initially loads, it's a good time to go ahead and call this function. But remember, since on desktop systems, headsets can be connected and disconnected, you'll also want to register for the VR Display Connect and VR Display Disconnect events. These events are actually past the VR display object that was connected or disconnected, but for simplicity's sake here, we're just going to use the same function. Okay, so we have a headset. Now let's go ahead and request access to use it. The first thing that we'll need to do is set up a canvas into which we're going to render. And then we're going to set up the WebGL resources that we're going to use to do our rendering. It's a good idea to do this when your page first loads, because then you can provide a preview experience to users as to what they'll see before they actually enter VR to give them enticement to actually do so. Okay, so here we've got this helper function called enterVR, and inside we call VRDisplay.requestPresent. We're going to pass in that canvas that we created up above and wait on the promise to complete. When the promise completes, we're going to go ahead and cue the animation frame callback using this helper function. Let's take a look at that helper function. I mentioned before about window request animation frame. This may be familiar to folks. This provides a callback at the display's refresh rate, the monitor's refresh rate. The VR display request animation provides a callback at the refresh rate of the headset. This might be 60 frames per second, but it could also be 90 or 120 frames per second, depending on the hardware itself. So it's very important that you actually use this request animation frame when presenting to the headset. Okay, so where do we actually call this function from? In this example, we're going to call it from a button handler. It's very important that we actually call the request animation frame function from a user-initiated action, because once the promise completes, the website actually has taken over control of rendering to the headset. It will have evicted any other experience that was previously presenting in the headset, and it starts getting pose data about where the user is in space. To prevent malicious websites from calling this API without a user's intended action being taken, this API is blocked on the user-initiated action request. And the promise will reject if invoked outside of such a callback. One other thing that Microsoft Edge does to protect our users is the first time you attempt to enter VR on a particular domain, we'll ask your consent to do so. Okay, so we've gotten permission to draw to the headset. Let's look at how we actually do that. The first thing that we're going to need to do is to call the getFrameData API. We'll pass in this VR frame data object that will then get populated with the pose as we mentioned before. It'll also have the matrices used for rendering, which we'll look at in a moment. This function can return false under several circumstances, so it is important to make sure you check the return value. For example, if you call it before actually request present completes successfully, it's not going to work, and you shouldn't use this data to render a frame. All right, so we have a good frame data. We're going to update the canvas size so that it's big enough to fit all of the pixels we need to draw. We're going to update the state of our scene and actually do the drawing. And then we'll submit the frame so that it actually presents to the headset. And then when we're done, we'll go ahead and queue that callback so we get called back again the next time we need to draw to the headset. Let's take a look at some of those functions in the middle. First, updating the canvas size. To do so, you'll call the getEyeParameters API, and this will give you the resolution of each eye. Then you'll want to set your canvas to actually be big enough. In this case, we're going to render the left eye to the left half of the canvas and the right eye to the right half of the canvas. It's safe to call these functions every frame, and in fact, it's recommended to do so. However, if you're not going to, at the very least, make sure you've disabled the logic that resizes your canvas when your page resizes. Okay, so let's take a look at drawing this VR scene. The first thing that we're going to do, as I mentioned before, is update the logic of your scene itself. You may be running physics simulation, you may have animations running, you may need to respond to user actions. This is a great place to do that. Once your scene is ready to go to actually be rendered, you'll set your viewport for your left eye, draw it using the matrices off the frame data, and then do the same thing for the right eye. Now, one other note before we move on from this section. It may come as no surprise to the folks in this room that PC users have a wide variety of graphics cards that they might plug their VR headsets into. As such, it may mean that when the user attempts to enter VR, the browser will need to switch graphics adapters so that it can do so appropriately. In order to handle this situation, to make sure that your content is viewable by all possible users, you're going to want to register for the WebGL context lost event. And in response, you'll just call prevent default on the event to indicate that you're planning on reloading your resources in the WebGL context restored event. You'll see here that we're using that same GL setup function that we used at the very beginning. Okay, so we've queried for the headset, we've requested access to the headset, we've drawn to the headset. Now it's time to get back out of VR. You'll probably want to add an exit VR button, similar to the sort of enter VR button you had. And inside the button handler, you'll call the VR display's exit present function to actually exit VR. But it's important to note that your site may actually be exited from VR without of your own volition. Another application could have taken over the headset. In Edge, the user could have pressed escape to return back to the browser, just like we do with full screen. Or the user could have switched tabs, or really any other reason. And as such, you'll want to register for the VR present change event. VR display present change event. Sorry about that. And in response, you'll want to cancel the window callback when you actually enter displaying to the headset, and vice versa, cancel the display's animation frame callback when exiting from presentation mode. And then go ahead and queue that callback. This helper function will make sure you get the right one. All right, now we know how to display WebVR content. We query for the headsets, we request access to it, we draw to the headset, and when we're done, we back out. So now you should know everything you need to know about WebVR, right? Not quite. Because if we think back to that imaginary hotel example from the beginning of our talk, the first thing that happens when users get into VR experience is they want to interact with it. It's the difference between being able to look around the hotel room and being able to find out more about the amenities that you see there. It's the difference between being able to look around where you are and point to a spot on the other side of the room to teleport yourself over to see the room from another position. The challenge is that users have a surprising variety of input devices they can use. There are motion controllers, mice, Bluetooth clickers, Xbox controllers, keyboards, or maybe just the headset itself is all they have. And solving this problem is probably the most challenging aspect of using WebVR today. So we're going to take a look at a couple techniques for targeting objects to make this simpler, as well as the feedback mechanisms to indicate to users that the action they're taking is on the thing they intend. And then we'll take a look at the APIs necessary to implement this behavior. Okay, let's look at how we target objects. The first type of targeting is known as gaze and commit. In this type of targeting, users target objects by moving their head around. And you cast a ray from where the user's head is in space in the direction they're looking and intersect an object in the scene. And the first thing that's hit is your target object. You then commit an action against that object via a gamepad button press, a mouse click, a keyboard press, or just holding your head steady long enough to pass some threshold. Now the thing is, when users have motion controllers, they generally expect to be able to use them. So in that model, you'll use the point and commit model. Instead of casting the ray from the user's head, you just cast it from the tip of the motion controller and follow the same logic using the motion controller buttons as the commit mechanism. All right, so we've talked about how you target objects. Let's take a look at how we provide feedback to users that the action they're taking is the one they intend. In this video, it's maybe a little challenging to see from here, but it's pretty clear in the headset. There's a cursor right in the middle of the screen. This cursor can be used for both gaze and commit, as well as point and commit type interaction models, and can also change its display depending on which object it happens to have interacted with to give the user a sense of what action might occur. In this example, we have a pointing ray. This pointing ray is drawn from the tip of the motion controller to where it intersects with the 3D geometry of your scene. Drawing a pointing ray is not recommended for gaze and commit. While it might sound cool to shoot a laser beam out of your face, it's actually far less comfortable than it sounds. In this video, we'll see how you actually observe motion controller button presses, as well as the motion itself inside the virtual world. This is very helpful feedback to users because they can't actually see their hands while in VR. It's also kind of surprisingly satisfying to press those buttons and watch them change on the screen. All right, we're in the home stretch here. Now let's take a look at the APIs that you'll actually use to do the things that we just looked at. The first thing to take a look at is navigator.getGamePads. This is a polling style API, and when invoked, it will return the set of currently connected gamepads and motion controllers. You'll iterate over the length of this array, looking for non-null items, which is important because controllers can be disconnected or reconnected at any time. And one thing to note, controllers won't necessarily appear in this array until either the user has pressed a button or has actually entered VR. This is a security consideration to make sure that users are taken care of safely. As a result, when you exit VR, the same controllers may either disappear or stop updating their pose data. So how do you tell the difference between a motion controller and a traditional Xbox-style gamepad within this array? The answer is the gamepad pose object. On traditional controllers, traditional gamepads, I should say, it will be null. For motion controllers, it'll have a pose object in there. And you can use that pose object to update the position of the controller in your scene, as well as the origin for your point and commit style targeting. When you don't have motion controllers available, you can use the VR frame data pose object to get the gaze rays origin from the user's head. But remember, don't use this data if the get frame data API has returned false. And lastly, let's take a look at how you use mouse clicks. You're going to want to request pointer lock and not just use the click without it. On some browsers, these mouse clicks might accidentally go to places outside your browser, the address bar, or whatever, which you can't see because you as a user are in the headset. On other browsers like Edge, the pointer data is restricted to only reach the website when pointer lock has been taken while in VR. To handle that first category of website, you will respond to the request present change event, or the VR display present change event, as we mentioned before, by taking pointer lock in response to entering presentation and leaving pointer lock when VR has been exited. On browsers like Edge, you'll register for the VR display pointer restricted event, where you'll request your pointer lock, and you'll release your pointer lock in the VR display pointer unrestricted event. These events roughly map to lifting up the headset and putting it back down, but there is an override with the Windows Y key that allows users to toggle the mouse behavior as appropriate, for example, in demo driver type scenarios. Okay, so we've covered how you target objects, how you provide feedback to users about the action that they are about to take, and we've shown you the APIs necessary to code it up. Congratulations, you are now a WebVR expert, and I'm going to hand this back over to Lewis to talk about some more things you might be interested in.
Thank you, Neil. So, you are now armed with all the knowledge you need to go back and create a fully interactive, immersive experience, which will consist entirely of black pixels. That's because something is obviously missing here. We've completely glossed over how to actually draw a 3D scene using WebGL. The reason we've done that is most websites don't actually use WebGL directly, instead opting for 3D graphics engines like Babylon.js, Three.js, ReactVR, and A-Frame. These engines provide layers of abstraction on top of the raw browser APIs, also offering structures, math helpers, and helpful effects, which you can use to build 3D experiences. And now with the advent of WebVR, these same libraries are adding support for viewing their 3D content in VR. We are very happy to share that within days there'll be support for Windows mixed reality headsets and motion controllers in all of these libraries. And I'm going to give a huge thanks out to all of the project contributors and maintainers for working with us to make this happen. Now, you may be wondering how to choose which library to start with. And the answer to that is, well, of course, it depends. Oh, there we go. Three.js is a lightweight 3D library. You define your scenes and geometry in JavaScript, which will give you fine-grained control over rendering. Three.js provides WebVR built-in, which means all of the API calls are handled by the library itself. And motion controller support is under active development. ReactVR. This is a great place to start if you have prior experience with React or are looking to add WebVR content to an existing React site. It's got the familiar declarative style of React framework, and you can use regular React components in VR, such as the text box, buttons, and images. You can also incorporate regular React libraries and tools, such as unit testing frameworks or data management libraries. And there's motion controller example code available, which allows you to integrate the controllers into a VR experience. A-Frame allows you to make a WebVR experience using just HTML. The library, once again, handles all VR setup for you. All you need to do is add entities with components, such as lights, meshes, etc., to those. If the inbuilt components don't quite do what you need, there's also a component registry where the community has uploaded their own, adding extra functionality. A-Frame has full gaze and commit support for our Windows Mixed Reality headsets, as well as full point and commit support for the Windows motion controllers as well. Lastly, we've got Babylon.js, which is a JavaScript-based 3D engine. However, you can also use TypeScript with this one as well. Babylon gives you a high degree of control over rendering, and it's still easy to use. You can add complete VR functionality with just a single line of code. Babylon has full gaze and commit support with the mouse and gamepad, as Nell was discussing before, plus point and commit support with our motion controllers. They've got extensive documentation online, and the Babylon Playground that hosts over 200,000 samples, and you can create your own. So what we've got here is a quick piece of sample code showing how you would make that hotel scene from before in A-Frame. Firstly, we create the scene. This one line here will initialize the 3D renderer and add all the VR functionality for you. Next, we add two entities to signify we want both left and right controllers to appear in our scene. Lastly, we just add a skybox, which has a 360-degree photograph on it. And there you have it, that's your scene. Next, we have this very same hotel example in Babylon.js. Once again, we start off by creating the scene. This initializes the 3D engine. Next, we tell Babylon that we want this to be a VR experience. This line here will initialize all of the controllers, add the Enter VR button to the page, and handle all of the events that the browser might evoke. Lastly, we add the skybox with that same 360-degree texture. Okay, so whichever approach you take, we have some suggested practices to keep in mind when authoring that WebVR content. Let's go through 4 considerations for VR application developers. Firstly, there's a wide variety of headsets. As Noel mentioned, They have refresh rates of 60 to 90 or even 120 frames per second. This means you as a developer only have somewhere between 16 and 8 milliseconds per frame to render both eyes. Oh, too quick. It doesn't matter that much if you miss the odd frame here or there, but a consistently low frame rate will drive away your users. Okay, so emulators, the simulator, and Magic Window devices are really great for rapid iteration and development, but they don't give you that visceral sense of actually being within a VR experience. So some interaction mechanics that you create for those simulators or on the desktop may work great, but once you actually try them in VR, it might not work quite as you thought. Now, since, as we've seen, the coding delta between adding VR and not is so small, it's a good idea to add VR in at the beginning of your project. This will mean any design and art decisions you make throughout your cycle will take VR into account, avoiding that costly rework at the end of the project scramble. Another important factor is how far things are away from your face while in VR. Just imagine in real life, if you hold your finger right up and close to your eyes and try and focus on it, your eyes are going to get tired after a little while. Now, the same thing applies in VR as well. Try and keep objects in your scene between 1.25 and 5 meters away from your user's focus. This also includes dialog boxes with text and the gaze cursor itself, which should be projected out into the scene onto the object you're gazing at. Speaking of dialogues and user interface, try and avoid locking it to the user's gaze. So what you don't want is it following them as they move their head. A good idea is to actually apply user interface elements to the controls themselves, or even have objects in your scene be the user interface. Lastly, you'll want to provide a mechanic to allow users to move around your scene. So teleportation is a great one. You can also use a dashing mechanic by pressing a button to move forward quickly. But remember to fade the screen down to black or just blur the edges a little bit to make it more comfortable for everybody. I've already mentioned headsets. They differ in terms of refresh rates, but they also have different resolutions. A mobile VR headset might have a 720p screen, which is shared between both eyes, whereas a desktop headset, such as the Windows Mixed Reality headset, will have a 1440 by 1440 resolution for each eye. Some further differences between the headsets are tracking capability. Some mobile headsets will only track the head's rotation, whereas others will track position as well in space. Additionally, the performance of the machine on which you're rendering the VR experience will vary greatly. Mobiles have a greatly different GPU power than your desktop machine. Both can run WebVR. So the best way to handle this is simply to test on a broad range of hardware. This includes also which browser you're testing on. Yeah.
Before we wrap up, there's one more topic we'd like to touch on. Virtual reality, mixed reality, augmented reality are evolving quickly, and the WebVR specification is still under development. Microsoft works very closely with the other companies implementing WebVR, as well as the community at large, to ensure that the WebVR APIs are web-friendly and ready for what's coming next. And to that end, there is a refresh of the WebVR API design currently underway. It's going to set the stage for some exciting new functionality to come. Stay tuned for these spec updates. Join us on the GitHub where we're discussing them, as well as join us for the Windows Insiders program to get the very latest access to the Windows Mixed Reality platform. We hope you found this introduction to WebVR useful, and if you'd like to talk to us more or learn more about our headsets or come check them out, find us upstairs in the booth after the talk. Thank you very much.